Okay, welcome everyone. Welcome to this fun seminar today. Today we are welcoming Ruth Misener. She's a professor at Imperial, and she's been collaborating with BASF, BASF, which is a major industrial chemistry company, and she's going to talk about her very interesting research. I met Ruth some years ago in a workshop we organized in multi-fidelity optimization in Warwick, and to be honest, I haven't heard of her before. And then after the workshop, I saw her name everywhere. So it was always I was looking at the wrong place, reading the wrong papers. And actually, I learned a lot by reading her work and all the interesting things she's doing. She's precisely working on the things that I think are interesting about optimization, that is expanding the frontiers of what you can do with optimization to problems that have unconventional features or unconventional requirements. So I think it's very interesting. Thank you.
Thank you very much, Manuel, for the really kind introduction. It actually went the other way as well. Like as soon as we met, I think we went into similar fields at the similar time and started publishing at similar times. Okay, so I'm Ruth. I really like to chat, and so basically, I have put the thing I wanted to say first, the second. And so if I do not get through my presentation, I truly do not care. It would be much more interesting to hear what you all have to say, because I already know my research. As Manuel mentioned, I work with BASF. If you haven't heard them, it's because you're not in chemistry or chemical engineering. They are the biggest industrial chemistry player on the market. They have been for the last 160-ish years, and they're actually responsible for the explosion in population that happened about 160 years ago. Because basically what happens is we have lots of nitrogen in the air. You take nitrogen out of the air and you put it on crops, and all of a sudden the crops grow better. That is them. It's the Haber-Bosch process. And they basically invented that 160 years ago, and they have been, since then, the biggest player. So they are a massive, massive company. And this is just some of the stuff that I do with their R&D. So I don't know everything about the company. I just play with some of the stuff that they like and that I like too. Okay. Perfect. Okay. So just first to mention, I'm presenting the work of three super smart PhD students. If at any point I refer to my work, I actually mean their work. Just really fun stuff that they have done. So just to give a general idea, because I really wanted to give a sort of chemistry style presentation here, because I know that you all are exceptionally good at sort of the fundamentals of AI. So I want to show you the kind of problems that it would be amazing if you all were working on too, because it's a monster big area. The kind of thing that I am interested in doing with BASF is this thing where we've got a chemist and a lab bench, and they're sort of improving things until they decide to scale things up, eventually scale up to the plant level. And there's all sorts of places that people with the expertise, such as what you all have, really could make a huge difference. So in terms of discovery, in terms of what molecule to develop, that's basically a generative AI problem. And we were making fun of some sort of approaches for this earlier, but ultimately it's what you want to do. It is a generative AI problem. Then I'm an optimization person. I'm interested in design of experiments. So where I will focus today is basically you've developed your molecule. Now you wish to sort of start thinking about how am I going to create it in the lab bench, and how am I going to isolate it? How am I going to make sure that it's the only thing that I have? Then there's plenty of really interesting transfer learning problems, as we were discussing, once we're trying to increase production. And then there's all sorts of multi-objective optimization problems. So tons of stuff that's really relevant for the kind of skills that you all have. And today, what my focus really is the optimization side. And the guy who is the boss of the people who I collaborate with, has this idea of what he calls autonomous research machines, where instead of a human going into the lab and sort of doing experiments to, for instance, optimize reactions or improve yield for a particular product or improve selectivity, you should instead have everything automated. And so I'll show you some of the bits where I've gotten to help towards that goal. Of course, that's a monster thing that my bit is small within that. I actually want to show you, again, because I know that you all are experts in this area. I think maybe Mauricio is online, in addition to Manuel and Julia, who are both in optimization. I know Mauricio and others are interested in optimization. And this is the BASF sort of public-facing open source access point to their design of experiments approaches. So I'm super interested in Bayesian optimization / design of experiments. They are too. They are taking, they are wanting to take advances from different groups and pull this into practice. And they are doing that through this tool, Bowfire. Bowfire is basically just a wrapper around Bowtorch. So if, I mean, maybe you look at it and you say it's not so different than Bowtorch. Really, the differences from Bowtorch are more along the lines of specializing things to the particular ways that chemistry problems are maybe different from problems that we'll see in other domains. And also separating, basically meaning that their backends go to sort of common structures in self-driving labs. So anyway, this is an open source software package. It is your way of possibly getting your stuff into BASF. I use it all the time. I am funded by BASF, so I am also, my PhD students are paid to put their things in, but it's a way to access them. A thing that's been fun is that it's not only with BASF, it's also with a couple other companies, and Bayer just joined as well. So Bayer is now contributing to this thing as well. So it's a nice way to get attention from everybody who's interested in industry in self-driving labs. The other thing to mention is that there's the academic interest, there's the industrial interest, and then where Bowfire has really sort of caught fire, if you will, is that there's a lot of startups in this space in terms of doing sort of optimization for self-driving labs. And what they've done is they know they have to get attention from the big players, from these big companies, to be able to get business for their startup. And so there's a bunch of startup guys who are now also contributing to this package, which I think is really fun. So anyway, that's my sort of sales pitch on this. I know that, you all have more than the skills to kind of contribute to this kind of work. And it's really just a question of, do you want to contribute? Is it worth your time? And if it is, that's the way in to this particular community. Okay, I'm going to go back now just briefly and show you what a chemistry setup would look like, and then sort of why I think this is interesting from a machine learning point of view. So just a picture of a bench. To me, this could be just about anything. But what is going on is you've got something super simple that's happening on this particular bench. You've got two reagents that are being pumped into a reactor. The reactor is heated, and then after you go through the reactor, there's some sort of inline analysis. Later on, there'll be sample collection, and then we can do some sort of offline analysis to understand better what it is that happened inside of that reaction. This is a super sort of old thing to do in chemistry. The sort of first papers appeared approximately 2010, but this has now gotten to the point where the big players are using this inside of their corporate R&D structures. And so it becomes something that, it's not just a couple chemists playing with it. There's a lot of push behind it. Hence the BASF interest. Now I know that, Manchester is a place where there's a ton of expertise in Bayesian optimization. And so let me just explain the the problem now in pictures to try to say what's so cool about this from a Bayesian optimization perspective. So first off, I get to choose the input chemical composition. That has a discrete aspect because I decide what things to put in. And then it also has a continuous aspect because I get to decide what amount of what things to put in. Then there is a flow rate. So there's the speed at which I'm pushing things through. There is the temperature profile in the reactor. Yeah, those are the ways that I can change the conditions. Of course, I can design the reactor itself, but that's not something I can change as I go along, right? Is that designing a reactor would be one problem. This is now the problem of I have the reactor and I wish to do a series of experiments. Okay, now I can get outputs. I can measure while things are going, all these experiments are going through the reactor, I can measure things like fluorescence or yeah, something like fluorescence I can measure, where I can take photographs of what's happening and I can get some information back. Then after we have passed through the reactor, I can do some sort of assays that are really nice, that I can say exactly what it is that came out of that reactor. Okay, blah, blah, blah. Why do I think this is cool from an ML point of view? First off, I've got features of an asynchronous batch. Basically, what's happening is each experiment in the reactor can be some sort of little droplet. So right here, I'm illustrating things as all these individual droplets. The other way to go through a reactor is what's called plug flow, where everybody you just all move along, but then you can sort of change the conditions and different plugs can be different experiments. But this asynchronous batch thing is that I can do this chromatographic assay on experiment 1, but experiment N is still, I have to choose what's going to happen first, right? So the batch aspect is that I have lots of experiments to choose before I get all the information back on experiment 1. So that's the batch aspect. The asynchronous aspect is that different, yeah, it's delayed in time. And then the delayed in time. And then the multi-fidelity aspect is related to the asynchronous batch aspect. It's that different information has different qualities in it. So what I want to know is ultimately what came out of that reactor. What I know while the experiment is happening in the middle is only what I can tell from pictures, which would not maybe be the actual information I want back. So it's a measurement of information that I didn't exactly want. So that's the multi-fidelity aspect, which is related to the asynchronous batch aspect. Then there's this path-based control aspect. And here, I don't mean quite control in the sense of control theory. What I mean is that I have to change things in a way that is conscious of where I have been and where I want to go. So basically, flow rate, for instance. Flow rate is something where everything is moving along. If all of a sudden I really increase the flow rate on experiment N, it's actually also going to change the flow rate on experiment K. Because what's going to happen is that flow rate is kind of like when crowds are moving, and if I'm in the back acting impatient and American and I start pushing people really hard, you'd better bet that the people up front are going to maybe feel it, or maybe somebody's just going to hit me and we're going to be done. So path-based control is that where I have been and where I'm going really matter. Another thing I mean by path is something where, so sometimes I mean you change something and you're changing some of the future experiments. Sometimes I mean that two experiments that are near one another have to experience very similar conditions. So for instance, droplet K and droplet K minus 1, good luck having them have different temperature profiles, right? They're going to have the same temperature profile. And if I wish to change temperature profile, I had better think about it in advance. Furthermore, this isn't, we were talking about distances earlier, this isn't something where the distances are Euclidean, because I know how to heat up a system much better than cooling down a system. This is one of the things from chemistry, if anybody has done thermo, is that heating up and cooling down are different things. Then we've got this mixed feature aspect. We've got integers and we've got continuous. We've got hierarchical decisions. Manuel was talking about this from some of his applications where you sort of make some decisions and then you decide on more decisions. And then you've got input constraints. So for instance, good luck having your fractions of your chemicals going in be different than summing to 1, right? Is that that's just what's going to happen. Okay, so this is mostly just sort of proselytizing the problem because I know you all are super strong, and it's just the kind of thing where the ML community has a lot to say. Okay. So this is our Beaufire framework, or rather, all of the algorithms that I will talk about have gone into Beaufire. And basically what's happening with this Beaufire tool is that you're choosing things like what molecule you're going to use, what things like temperature you're going to use. I like Bayesian optimization, probably just because I like doing research in the area. But chemists who have been around for quite a long time, they like these sort of classical design of experiments approaches. And what Beaufire does is sort of does both at the same time, basically to try to increase confidence. We give a proposal for the next experiment, and we iterate. And I already mentioned that basically the reason for people like you being interested in these sorts of things is that they've already made it so that you can connect internally to what they're doing. Okay, and this is just to say that I've read the literature, and I know that all those ideas that I presented are not new in the sense of there's tons of amazing ML research that has been done over the years, kind of addressing each of these issues that I mentioned and that I somehow wish to solve. So acknowledge that there's a lot of stuff that is there. Where I like to do research is sort of these problems where you have many of these sort of complications all at the same time, and somehow maybe some of the approaches would so go towards targeting just one issue that then you'd have to rethink them once there were multiple issues at stake. Also, I go chemistry, because I collaborate a lot with this chemistry company, but it's worth it to say that there are these other applications. I like chemistry because it's just so tough, and there's so many problems that you're being thrown all at the same time. But for instance, this asynchronous batch and path-based control type thing, you can think of that also if you're doing sort of pollution sensing or something like this, is that if, for instance, I am driving a boat on a lake and I wish to figure out where are the sources of pollution, that boat is not going to ping across the lake in the way that Bayesian optimization will. It will go from one place to another, and you had better want to go all the places that you are going on your path. Then I did not come up with this collaboration. Two of my PhD students went to this AI for Good Dodge tool, and they came back with this collaboration with this team in Uganda. And what they are doing is, in African cities, you have maybe fewer pollution sensors than we have in London and this kind of thing. And so the idea is to have people either pollution sensors on buses or pollution sensors sort of driving around, which makes your distances thing even more tough. So I don't know, we've played with this some, and we have all the challenges that you mentioned. We should talk more about that. Okay. But going back to the chemistry example, I'm going to take just two of these, put them together for a paper that I thought was really fun that we published a couple of years ago. Put together this asynchronous batch aspect and this path-based control aspect. And it's actually going to be particularly this sort of microreactor example. Okay, so assume everybody knows how Bayesian optimization works because there's just so many people here who are ridiculously talented in the area. I am maximizing a function. Yellow is where I want to be. I expect Bayes-opt to kind of jump around, right? Fine, that's what we expect. Just to sort of skip to the end and give an idea as to what we want or what we did. Maybe it's not, not trying to claim it's the perfect thing. What we have is an algorithm that picks where it wants to go. So first it's trying to say, what are all the points that I wish to visit? After I know what points I wish to visit, I choose a path through the search space and I follow it. And so hopefully in our formulation for this particular problem, distances in terms of getting from one piece of the search space to the other, we were penalizing as a cost. This was consistent with our examples because you can switch your chemical composite, you can switch a lot of your conditions, like you can switch flow rate. It's just that maybe then you have to wait some period of time before your experiments mean anything. And that time period of wait is your cost, for instance. Okay, now this is done with respect to Euclidean distance. As Julia knows much better than me, distance is sort of a sneaky thing. So just to mention that what we also did is that we can measure a lot of different distances. What I'm showing on the right is now Bayesian optimization for the exact same function as before, but I am not penalizing the up and down axis. I am only penalizing movement on the left-right axis. And where this would be relevant is that something like switching chemical composition, you can do pretty fast if you're not going to change the flow rate. If you're going to change the flow rate or if you're going to change the temperature, you're waiting for equilibrium in some sense or quasi-equilibrium, and that's a real pain in the neck. So different distances mean different things. We also have it so that a distance up can mean something different than a distance down. That is relevant for something like temperature, where heating something up is not the same as cooling something down. Okay. Sorry, I feel like I come to like the world-class machine learners and give you a chemistry presentation. It's just that you guys would be awesome at this. So there you go. All right, so just to prove that I do math every once in a while, I've got a Bayesian optimization problem. I wish to optimize it. For every query, I get a noisy observation back. But because of time delay, the data set at my iteration is such that I do not have all of the pieces of information that maybe I wished I had. And then I have to pay to change experiments. There's some cost function going between two experiments that I have to pay. In my application, this is something like time to switch between the two experiments. There are applications where this input cost thing is a bad assumption. Reason being is that maybe you just can't move from point 1 to point 2 in the next time period. There is some sort of constraint, and it's not a cost, it's a constraint. In that case, Jose has some follow-up work that is tackling that kind of thing using more of an RL style approach. But this is for the instance where I can change the experiments, I just got to pay. And then we're going to fit a probabilistic model for decision making, and we're just going to choose Gaussian processes. Okay, so I will now show you what our solution is. If you have better, I'm always happy to hear. Either tell me or I'll find out in a few months or whatever. We like these approaches that do Thompson sampling just because it's easy for me to use. So if anybody hasn't seen Thompson sampling, what you're doing is you're using the interpretation of Gaussian processes that it's an infinite set of functions, and you're just pulling functions out. Then for each function that I pull out, I'm going to optimize over that function. Most of the samples I pull out will be in areas with high mean. By the randomness of the GP, some of the samples will be in areas of high uncertainty. Now I have a list of places that I wish I could visit Where this might be a good option would be in places where the batch size is going to be extremely big, because basically with a Thompson sampling is awfully cheap. I can get these samples really fast. I can optimize them really fast. And once we have them, we have a list of places we want to go. It's a long list. I can get it pretty fast. So that would be why I would use that, and not, I mean, there are more expensive look ahead techniques that think through things in different ways. Once I have a list of places that I wish to visit, I then can solve a traveling salesman problem. I was originally trained in mixed integer optimization, so I'm always pleased when, like, you have to solve a traveling salesman problem to get from point A to point B. And anyway, so we solve a traveling salesman problem, and then we have a path that we're going to follow, done and dusted. Okay. Now, what was so funny, and I mean, there's maybe, I've had some people actually anticipate this, and so I wouldn't be surprised if some of you had anticipated this problem already. And I thought this was great. And the PhD student came to me and was explaining to me, you know, this doesn't actually work. And what was crazy about it is, what I like so much about BASOpt is that it's a global optimization method. And all I had done with this set of ideas is I had taken a global optimization method and I had turned it into a local optimization method. And I'll show you why. So what happens is you have all of these samples and you have this path that you've planned. And so you're going along your path, and then you have updated information. So you update your surrogate model, you update the path that you want to follow, and again, you start following all the points that you want to visit. Where your problem comes is if your number of samples or your time delay is such that there are always points that are near the best solution you have already found that you wish to explore. You might just keep exploring them forever for no good reason, or actually for a good reason, because our algorithm isn't designed so well. So what happens is we can get stuck. So we've got this dotted line, and there is an optimum over at x is equal to 0.8 that is better than the local maximum that's at x is equal to 0.2. And what's happening is I want to be able to find that optimum at x is equal to 0.8. And I do my Thompson sampling, and I say, okay, path, and I start walking towards x is equal to 0.2. As I'm walking towards x is equal to 0.2, I get the information back about the function. And the Thompson sampling is always going to have some exploitative examples in the batch. So I say, okay, I'm going to do the exploitative ones first because they're nearby. And I keep going nearby, and I keep going nearby, and I never stop. I will just sit there. And that this isn't surprising, right? Is that I took a global optimization algorithm, I turned it into a path-based algorithm, but that's a local optimization algorithm. So, I mean, that's what we know from first order optimization. That's not so tough. I should have understood this. The way that Jose fixed this is that he developed something called point deletion. So, sort of alert, I'm going to introduce a parameter and then try to show you that the parameter wasn't very important, and also that we can get rid of the parameter. And so what we're going to do is that we have this actual optimization path that we're going to take. Then we have our plan of where we're going to go next. Then we get the updated information, update our surrogate model, update the Thompson sampling, update where we want to go next. That's all of the points in the middle. But you can see if I kept all of the points that now I have as my list of things where I'm going to go, I would just sort of stay exactly where I was at x is equal to 10 and just sort of explore in that little region. And so what we will do is we will, from the many points in the Thompson sampling, we will pick points to delete. The reason that we will pick points to delete is that we know that Thompson sampling is going to be much too exploitative in problems like this. We will ignore those, and then off we go exploring problems that are hopefully different. Okay, I introduced a parameter. I don't like to introduce parameters, so let's talk about what this parameter means. So first off, I made up a new metric, and I win on the new metric, which is, you know, classic academic, right? So regret versus cost. Cost is my metric, so if I didn't win on it, you better think I'm an idiot. The red is all of our implementations with this parameter changing. So with this parameter going from 0, which is just sort of randomly delete things, to 1, which is a radius for deletion, and to this sort of L, which is use hyperparameters from the GP to delete. So they're performing roughly the same. So I've introduced a parameter, and then I'm trying to motivate that it's not that important. So cost is the thing I made up. It's how expensive it was to get through the experimental campaign. So ours, cost versus regret, we're doing well. Great. Okay. Regret versus iteration. I don't argue that ours is better. They kind of all look the same to me. What I think is useful to note here, and I am very sorry if somebody's red, green colorblind, because I've been a bit useless here. And the many in red are all of ours. The green one is Thompson sampling. What I really like about this middle graph is it says that we're roughly performing with Thompson sampling. So we haven't, because basically what we were is that if we're just doing cost, or you're just doing regret versus iteration, sort of classic Bayes opt, you'd better hope we're not too different from Thompson sampling, because if we're different than Thompson sampling, then we sort of, by choosing this path, we might have messed everything up. So that's good. Then the final thing that we have is that we have, again, cost, which is, again, our metric. So you better hope that we're going to be low on it, versus iteration. And here, the reason that I like it is that ours is in the red over and over again. It is somehow similar to the yellowish, the dark yellowish line. Dark yellowish is a Sobel sequence. If I want to do space filling, I'm going to use a Sobel sequence, and then I'm going to choose one Sobel sequence, and I'm going to solve traveling salesman to follow all the paths between the Sobel sequence. So cost versus iteration, this is not thinking about the objective of regret, it's just thinking about how to explore space. What I like about our algorithm here is that we are roughly as space efficient as Sobel, which I like. Cool. I have no idea how long this seminar is. 40 minutes? Okay, perfect. Basically, as I mentioned, I just stop when people tell me to stop. I only say the things that are, any comments on this, how I could do it better, want to know more about the application so that you can knock it out of the park. American baseball metaphor, not working. Okay. Then I'll give you a 3-minute intro to the other stuff that we've done. I won't do that one. You guys know way too much multi-objective optimization. There's tons and tons of expertise here. Multi-fidelity is super fun. This was, again, I come and talk to like the best machine learners, and I just tell you about chemistry problems, just to convince you to do it. But these kind of multi-fidelity problems, as I see them often in the literature, in the ML literature, are often about, maybe like training an ML model or something like this, where I train a neural network for a short time and I get one answer, train a neural network for a longer time, get a better answer. Maybe by doing experiments on the things that didn't take long to train, I can know how to set up my neural net when I give it a long time or something like this. And I hear all of these applications, and the applications sound difficult to integrate. In chemistry, they seem extremely relevant, and it seems like all of the multi-fidelity things that I read are very immediately applicable to chemistry applications. So I'll give you just one example. batteries. My colleagues at BASF want to design batteries for electric cars. That is something where it takes forever to do experiments on a new pouch battery. You've got to make the thing. It's expensive to make. You've got to do experiments on the thing. Blah blah blah. Would be awfully easy is to put the same material in that you wish to do an experiment on into a coin battery. That's the kind of thing that you put into your watch. And if you were doing an experiment on a coin battery, I guess not watches anymore. Watches from when I was a child. If you're doing the experiment on the coin battery, the way the material behaves is dependent on the geometry of the object. And so these are two different things. What we did with BASF was basically to step back and look at all of the ways that the machine learning community has thought about multi-fidelity, and then sort of make some proposals or give some options rather for how the chemical engineers can follow on this. It's gotten a lot of traction, and whenever I talk to real chemists, they're all like, they're so excited about multi-fidelity. And I know that there's an awful lot that chemists are doing where I go and I talk to them about their multi-fidelity work, and it's cool, but they're really missing a lot of what could happen in the literature. So anyway, just trying to say, find yourself a chemist friend. All right, basically what's going on, if you haven't seen this thing before, which I assume most people have, I've got something like the composition of my material down here. And then I've got something like the performance of my battery up here. And I've got two surrogate models that I'm learning. One surrogate model is how is what I think about what data I've gotten about the high fidelity experiments. This would be on the pouch battery, and some on the low fidelity experiments. This would be, for instance, on the coin cell battery. Then, and this is not my work, this is, of course, 10 years old NeurIPS, what you can do is that you can combine you can get an acquisition function that is somehow the combination of these two pieces of information, and you can decide where to sample and at what fidelity to sample. What our engineering contribution was actually pretty simple. There's an awful lot of really beautiful multi-fidelity works that are out there, and basically each of them would require that you would use one specific acquisition function or something like this. All we did was to do a very simple sort of engineering approach where we said, why don't we just give people more options to try to open up what exists in the Bayesian optimization literature to the chemists and the chemical engineers? And so we looked at two multi-fidelity approaches. One was based on variance, one was based on information. And we looked at several sort of batching possibilities. We basically, using either a variance-based approach or an information-based approach, we decide which fidelity to sample, and then at what point. And the only thing I am trying to show here in my little graph is basically that what we did is we showed heterogeneity in terms of some things being better than others at different times, which makes sense in engineering problems, is that we all know this, right? Is that different approaches work better or not in different engineering approaches. But the reason I present something that's entirely engineering to people who are so good at fundamentals is that it really is just kind of a step back, and like the kind of fundamentals things end up really mattering for these kind of applications. And there's definitely room for more fundamentals here. Good. Why don't we stop there, and I'll take any questions and or let you all get on with your day.
Thank you.